Welcome to your tutorial on isomers, specifically geometric isomers and constitutional, otherwise known as structural isomers. Before I delve into what these two isomers are, I just want to quickly talk about what isomers are in general, okay? And so isomers are basically molecules that are very similar to one another. They have the same atoms, all right, but they are slightly different. The thing that makes them slightly different is the fact that they have a difference in geometry or structure. And so structure basically is going to be to do with how atoms are bonded to one another, whereas geometry is to do with how something is spatially arranged or how different the 3D orientation is between two molecules. Something that I like to refer to as a little analogy to do with eyebrows. And if you're someone who gets your eyebrows done or plucks them themselves, I don't know. Eyebrows, this is the rule, okay? Eyebrows are meant to be sisters, not twins. You don't want your eyebrows looking absolutely identical. This is not something I've come up with. It's just a little beauty rule that I've heard of. Eyebrows are meant to be sisters, not twins. Similarly, isomers, they're also kind of like sisters, not twins. So, hopefully that analogy puts it into a bit of perspective on what isomers are, but I'm going to go into more detail with more chemistry examples. Okay, so the two different isomers we'll be learning about are geometric isomers and structural isomers. So we're branching off into these two types. Let's start with, I don't know, what should I start off with? I'm going to start off with geometric isomers and then we'll move on to structural. Feel free to take notes as you go. Pause the video if you need, and hopefully you'll be able to follow along. So geometric isomers, these isomers have the same types of atoms, and they're bonded in the same pattern to the same atoms. The thing that makes them different, however, is their orientation in space. As you can see, I've drawn two stick figures. Each stick figure is holding something. In the left hand, we've got an orange. In the right hand of each stick figure, we've got an apple. And so that meets the first criteria of a geometric isomer. They have the same number and types of atoms bonded together, okay? In this case, it's apples and oranges. The thing that's different about them, as you can see, is one is standing upright and the other is standing on their hands, all right? And so you can see that the 3D spatial arrangement is the thing that's different about these two stick figures. This is why they're geometric isomers, because of the 3D spatial arrangement differences. The number and type of atoms and the bonding pattern is the same. So this is a very loose example on what a geometric isomer is. A more chemistry related example are cis-trans isomers. What are cis-trans isomers and how are they geometric isomers of one another? Well, let's start off by going over what a cis isomer is and a trans isomer is. So if we look at a cis isomer, we can see over here that we've got two carbons. They're held together by this double bond. And on each carbon, we've got a hydrogen and fluorine. Okay? And so what we notice is if we were to draw this dotted line as a little bit of a plane between this double bond, we can see that on one side of this double bond, we've got the same type of atom. We've got hydrogens on this upper side of the double bond. On this side of the double bond, we've got two fluorines. And so because we have the same type of atom on either side of the double bond, horizontally, okay, not vertically, horizontally, this is what makes it a cis isomer. On the other hand, as we can see here, we've got a trans isomer. And so this is geometrically different because we can see here, first of all, that the atoms are actually the same as this molecule here. They're even bonded to the same thing. They're bonded to the same atoms. So they have the same pattern of bonding. We've got the same atoms as this molecule here. But can you spot the difference? The difference is, if we look at it horizontally, if we were to slice it horizontally, on one side of the double bond, we've got different atoms. So the actual definition of a trans isomer is that you've got the same atoms, you've got the same groups of atoms on different sides of the double bond on another carbon. All right, and so that is the definition of a trans isomer. Look at this hydrogen. It's on the opposite side of this hydrogen, which is bonded to another carbon, the other carbon in this double bond. So that is what you need to know, the definition of cis-trans isomers. And so these are geometric isomers. These are good examples of geometric isomers because they have the same atoms. They both have the same atoms. They are bonded to the same things in the same order, but they have different spatial arrangements to one another. And so if we were to look at the criteria on how to get cis-trans isomers, there are two criteria that you really need to remember. So take note of these. One, the first criteria is that you need to have a carbon-carbon double bond. You need to have this double bond because these double bonds are rigid. You cannot twist them. And so this double bond makes sure that you don't have any spatial rotation. You're not able to twist this double bond. And so because you're not able to twist this double bond, you're not able to rotate these groups in any way. That's why you're fixed with either a cis isomer or a trans isomer. You cannot switch this trans isomer into a cis isomer because of that rigid double bond. It's either one or the other. So you can get a cis or a trans isomer as long as you have this carbon-carbon double bond. So that is the first criteria. The second criteria is that each carbon in that double bond has to be bonded to two different groups of atoms. So you can see here, each carbon for each isomer is bonded to a hydrogen and a fluorine. Each carbon is bonded to a hydrogen or a fluorine. And so that's why you're able to get either a cis or a trans geometric isomer. You're not able to get the same result if you had the same groups on each carbon. So this is when we're looking at it in the vertical plane, like this, okay? You want each carbon to have different groups. You don't want the same groups, because let me show you what happens if you have the same groups on each side. So here we have it. If I were to have this molecule over here and try get a cis or trans isomer, I actually wouldn't be able to meet these two criteria. Even if I wanted to do anything to this molecule and maybe swap these around, it wouldn't make a difference. To have to swap either of these atoms, you wouldn't be able to get a cis or trans isomer out of this. You'd actually have to make sure that the groups of atoms are different on each carbon. And that's basically this example here. So this is why it's important to have different groups of atoms on each carbon. All right, and so that is basically everything about cis and trans isomers. You need to make sure that you know the two criteria of this type of geometric isomers. So now that we've covered what geometric isomers are, hopefully you've got that down packed. Let's look at structural isomers. What are they? Structural isomers, they also have the same number and the same types of atoms, but the bonding pattern of the atoms are different between each molecule. So this is the thing that makes each molecule different in a structural isomer. It's the pattern of bonding between atoms. And so here's an example. We've got structural isomers, primary. Oh, I feel like doing a little bit of an analogy. All right, so let's do another little analogy. If I were to have Lego, I love Lego, and I was building a little bit of a wall, okay? So I've got 3 blocks and I've got 3 colors. I'm going to build another wall with the same blocks, okay, right over here. This time, as you can see, I'm arranging them in a different order. And so this is an example of structural isomers because I can see that one wall over here has the same makeup. It has the same types of atoms or blocks that make up this wall as this one. However, the thing that makes it different is the arrangement of these actual Lego pieces. So they're bonded in a different pattern to one another. And this is what makes them structural isomers of one another. And so an actual chemical example would be primary, secondary, or tertiary alcohols or haloalkanes. So what do I mean by that? Well, I want you to know, this might be recap for you, that alcohols are anything with an OH group, and haloalkanes are anything that have atoms from group 17 of the periodic table. So that could be bromine, that can be fluorine, it could be chlorine, or it can be iodine, and so on, okay? And so here we have it. What are primary, secondary, tertiary alcohols or haloalkanes? For the purpose of this video, I'm representing haloalkanes or alcohols as an X, so don't assume that's an atom from the periodic table that I'm using here, all right? And so what do I mean by primary structures or isomers? A primary haloalkane or alcohol is when that functional group is bonded to a carbon that is directly bonded to one other carbon, as you can see here. A secondary isomer would be when this functional group is bonded to a carbon that is directly bonded to 2 other carbons. So it's all to do with what this carbon that is bonded to the functional group is bonded to. A tertiary isomer, as you may have got the gist of it now, is when this functional group is bonded to a carbon that is not bonded to 1 or 2, it's bonded to 3 carbons directly. So it's all about this carbon and how many carbons it is bonded to. And you will be expected to draw these. There have been questions that have popped up in the past, and so make sure you know how to identify and draw them and explain them. So there we have it. I need to write the definition here for this tertiary one, but I've explained it, so make sure you get it down for your notes if that is what you're missing. All right, and so here we have it. We've got structural, geometric, isomers. We've gone through a few analogies. I hope this made sense. Now what I want you to do is maybe take a little bit of a break. Go and find the link for the quiz that I've made for this section of notes. Test yourselves, see if there were any parts that you zoned out at, and go back to this video and search for those answers, because it's important to understand every little bit in here so that you can tackle some exam questions. All right, with the notes that we've just covered and the understanding of isomers, we can now start to apply that knowledge to a few exam questions. And so I've collated the exam questions which tend to pop up prominently. They just kind of repeat them over and over with different contexts. And so this is one type. So to be able to distinguish the difference between structural and geometric isomers is what we have to do here. We can see that we're dealing with butene, and it can be displayed in different forms of isomerism. Part I is asking us to circle the form of isomerism that exists between molecules A and B. So, are these structural? This is one category, structural or constitutional, that's one category. Are these structural isomers of one another, or are they geometric isomers of one another? If you need to revise again on what structural isomers are and geometric isomers are, please scroll to my notes, scroll back to this video, and have a go at testing your understanding again. But pause this video and take some time to decide what type of isomerism is happening between these two molecules. Is it a structural isomer? Are they structural isomers of one another, or geometric? Alright, so assuming that you've paused and you've given this a go, remember structural isomers have the same types of atoms in each molecule and the same number. The thing that makes them different is their arrangement. Let me convince you. We've got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens in molecule A, and we've also got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens in molecule B. We've also got 1, 2, 3, 4 carbons in molecule B and 1, 2, 3, 4 carbons in molecule A. And so same atoms, same types of atoms, and we've got the same number of those atoms on each molecule. The thing that's different about them is how they're bonded in each molecule. Okay? And so here we have it. It's a structural isomer because it's got the same types of atoms, same number of atoms, but they're just bonded in different patterns, in a different pattern to one another. And remember, an example of, if it were to be a geometric isomer, it would only be between cis or trans isomers. Okay, because that's the example that I gave earlier in my notes. Geometric isomers only occur between cis and trans, which look like these over here. Okay, so molecule A and B cannot be geometric isomers. That means it must be structural. Part I. Circle the form of isomerism that exists between molecule B and C. Again, pause and see if you can do it yourself, and then play this video again. So as I said before, we have geometric isomers, and geometric isomers are basically either cis or trans isomers. That's the example that we're dealing with in level 2. And so, as you can see here, we have a cis isomer here and a trans isomer here because of these groups being on opposite sides of that double bond and these groups being on the same side of the double bond. And so we've got an identification of cis and trans isomers. And cis and trans isomers are examples of geometric isomers because of their differences in spatial arrangement. And so that is the type of isomerism that is occurring between B and C. Moving on, we've got 2019. Refer to the compounds in the table below to answer these questions. So the first part, we have to draw and name 2 geometric cis-trans isomers of compound A. This is what we're focusing on. Explain why compound A exists as a geometric isomer while compound B does not. Okay, so let's start off by identifying the cis and trans isomers of compound A. Go ahead and do that and then come back and play this video to see how you've gone. Okay, assuming that you've gone away and done that, you should have gotten as your cis isomer this over here and your trans isomer this over here. Now it can be hard using a linear structure and trying to convert it into this, but you always have to make sure when you're drawing your cis and trans isomers, focus first on getting your carbon-carbon double bond in the center of your diagram. This is my tip for you, okay? And then you can worry about the other atoms. And so here we have it. I've drawn these two carbons and they're bonded together by this double bond. The next thing I'll draw on are the hydrogens. And so for a cis molecule, I need to make sure that these hydrogens are on one side of the double bond horizontally. So I'm going to draw one over here and one over here. Then I have to focus on the CH3s, okay, because these are bonded to the carbon. I know it looks like it's bonded to the hydrogen, but it's actually indicating that it's bonded to the carbon, okay? So don't let that confuse you. It's all right if you didn't quite get there. This is all good learning for next time. So I've got these carbons bonded to the CH3 groups, which are on the same side of this double bond over here in the horizontal plane. And so that is the cis isomer of this molecule. And so the trans isomer, as you can see over here, is I've popped the CH3 groups on opposite sides of the double bond on different carbons. And then the hydrogen groups are also on opposite sides on different carbons. So there we have it. A cis isomer and a trans isomer of compound A. It just takes a bit of practice, but you got this. All right. So next part, explain why compound A exists as geometric cis-trans isomers while compound B does not. Okay, just to sort of put this into a diagram that we can easily sort of understand when we look at, because I know looking at it linearly is a little bit tricky. If I was to draw it focusing on these middle carbons as the central part of this diagram, and everything else is up here. It's pretty similar to compound A, but what's the difference? What is the difference? I've kind of made it clear to you. The difference is that there is no double bond between the carbons. And so what is the reason for the double bond that I talked about? The reason for a double bond is to stop rotation of these groups around these carbons. And so because I don't have a double bond, I've only got a single bond, these groups of atoms can actually twist around into different orientations and form cis or trans in the one molecule. You cannot get a fixed cis and trans, okay? And so basically that cancels out the possibility of having cis or trans, even though you can twist them into each form. Technically, they don't have a reference point in space. They could be either whatever sort of fluidly cis or trans, okay? And so that defeats the purpose of isomers because they can change into one thing or the other. So you can actually not get cis or trans because you need that rigid double bond between the carbons, okay? And so what can we write about when we're comparing compound A and compound B? Okay, well, I want you to give it a go. You need to I would explain compound A, state the two criterias that are needed for a cis or trans isomer, and be specific to the actual groups in this context, and then go ahead and explain why compound B cannot, based on what I've just explained to you. Have a go. and then we'll see what I wrote. Okay, assuming that you've gone away and done that, let's scroll down and look at what I've written. I'll read it out to you, and then you can add things to your answer and make some adjustments. Compound A contains a rigid double bond. Let me get a larger highlighter. Different color. Compound A contains a rigid double bond between the two carbon atoms and therefore prevents the spatial rotation of the H groups and the CH3 groups. So can you see how I'm specific to the actual chemical compound? Don't just say different groups. You need to be specific with the atoms that are bonded to each of the carbons. Be specific about that as well. Secondly, this is the second criteria, compound A has two different groups of atoms, and I've specified that here again, bonded to each carbon atom. Therefore, compound A fulfills both requirements of containing a double bond and different groups of atoms attached to each carbon to form either a cis or a trans. Compound B does not form a cis or a trans isomer, even though the second and third carbon atoms have two different groups bonded to each carbon. It doesn't contain a double bond between the carbons. This means the groups bonded to the two middle carbons are free to rotate in different spatial arrangements without being confined to cis or trans isomers. And so that is how I've explained it. You need the keywords. You need to be very specific about how you're explaining things and the way you're explaining things. So make sure you have the right idea, make sure you're very specific to the actual context, make sure you're explaining what is on each carbon and how many groups. All these little details matter, okay? So this is your moment to be a bit of a perfectionist. Add those details, don't be vague, okay? Pretend you're explaining it to someone who absolutely has no idea what's going on. All right, next question. I'm pretty sure this is the last one that I have for us today. And so 2018, look at that. It's asking us to we're asked to draw the different isomers, specifically structural isomers of this molecule here. Okay, and so can you see how structural isomers are always to do with primary, secondary, and tertiary, and geometric isomers are to do with cis and trans? There we go. So how do we draw a primary structure? Well, remember, in a primary structure, the functional group of concern has to be bonded to one of the carbons that's bonded to one other carbon. So the way I like to draw it, I know I've already drawn it, but I like to start off by drawing, I like to start off by drawing the carbon skeleton. So this says that there are 4 carbons, so I'll go ahead and draw 4 carbons bonded to one another. Then I've got 9 hydrogens bonded to each carbon. And remember, carbon has 4 bonding sites, 4 possible bonding sites, and all of them are bonded. And so chlorine has to be bonded to one carbon that's bonded to just one other carbon. And so I would put the chlorine on the end, okay, because it's bonded to a carbon that is bonded to one other carbon. And so what I've drawn here is this. Take time to see if you can draw a secondary and tertiary isomer, and then come back and play the video and see if you got it correct. Okay, assuming that you've done that, welcome back. Here's what you should have gotten. This right here is a secondary haloalkane because it's bonded to, whoops, I just ruined my own little diagram. It's bonded to a carbon. This chlorine is bonded to a carbon that's bonded to 2 other carbons. And a tertiary haloalkane is bonded to a carbon that is bonded to 3 other carbons. Basically what I've done is I've taken this group over here and slotted it under this carbon over here, CH3, to make sure that this carbon is bonded to 3 other carbons. And there we have it. That's how simple it is, team. And if it's not simple right now, all it takes is a bit of practice. And if you look at the past exams, you can see that they're basically very similar to these ones, but different contexts. Please make sure if you're attempting any past exam questions, you take some time to go over them with me, okay, so that I can give you feedback and nitpick any details that you may have missed or anything that you might have not caught in yourself. Okay, it's good to get another pair of eyes to check over it. So please email them to me or come see me in person. Okay, so that's the end of this tutorial. All the best.